Imagine a star so dead that astronomers expect its lighthouse beam to fade into silence, and then years later, the beam speaks again. That is the mystery behind a neutron star reported to keep producing radio pulses after it seemed to have reached the end of its active life. A neutron star is the crushed core left behind when a massive star explodes. It can pack more mass than the Sun into a sphere about the size of a city. Its gravity is extreme, its magnetic field can be enormous, and if it spins with the right orientation, it can sweep radiation across space like a cosmic lighthouse. When that beam crosses Earth, radio telescopes detect a pulse. Not a sound in air, not a message. A pulse of radio energy arriving with a rhythm. For many neutron stars, that rhythm slowly changes as the star loses rotational energy. Over long periods, some are expected to become harder to detect or fall below the conditions needed to make regular radio pulses. Astronomers sometimes describe this as crossing a death line, though the phrase is a simplification, not a sharp physical border. So when a neutron star appears to pulse after it should have quieted down, it matters. It does not mean the star came back to life in a human sense. It means the engine that creates the radio beam may be more flexible than our simple models suggest. Maybe the magnetic environment changed. Maybe the beam became visible from Earth again. Maybe our idea of where the radio emission stops is incomplete. What is known is the signal repeated radio pulses from a compact stellar remnant. What remains uncertain is the exact mechanism keeping them visible. The takeaway is simple. Even a dead star can still surprise us, and to understand why we need to listen to the pulses themselves. The strangest thing about a neutron star pulse is that it can cross the galaxy without making any sound at all. Radio waves are a form of light, like visible light, but with much longer wavelengths. Your eyes cannot see them. A radio telescope can. It acts like a giant ear for electromagnetic waves, collecting faint radio energy from the sky and turning it into measurements. Scientists can study when a neutron star is a pulsar. It is not usually flashing in every direction. The common picture is a beam sweeping around as the star spins. If Earth sits in the path of that beam, our instruments receive a pulse every time the beam points our way. That rhythm can be astonishingly steady. Some pulsars are so regular that they become natural clocks. Others are messy. They can fade, brighten, skip pulses, or switch between different radio states. That behavior is one reason astronomers are careful before claiming they understand a neutron star completely. Detecting a weak pulse is not as simple as hearing a single ping. Space is noisy. In radio light, Earth has radio interference. The signal may be faint, scattered by material between the stars, or visible only during certain observing windows. Astronomers compare repeated observations, check timing patterns, and separate real celestial signals from local noise. What is known when the evidence is strong is the pattern pulses arriving from the same place in the sky with timing that fits a spinning compact object. What can remain uncertain is why those pulses appear, vanish, or return. This is why a revived or persistent pulse is so interesting. It is not just a dot on a screen, it is a clue about magnetic fields, charged particles, and extreme physics around a crushed star. The memorable idea is this radio astronomy lets us study objects we cannot touch by catching whispers of light too long for human eyes. And sometimes, those whispers refuse to stop. A neutron star that keeps pulsing after expected silence is not just an oddity. It is a test of how well we understand dead stars. Astronomers build models to explain when pulsars should turn on, how they slow down, and when their radio beams should fade. Those models are useful, but they are simplified maps of an extreme place. Near a neutron star, gravity is fierce, magnetic fields can be incredibly strong, and charged particles may be accelerated in ways no laboratory on Earth can fully recreate. So, a surprising pulse return forces a careful question: did the star truly cross into a quiet stage, or did our model draw the boundary in the wrong place? One possibility is that the radio engine can operate under weaker or stranger conditions than expected. Another is that the beam never fully stopped but shifted, weakened or pointed away from Earth before becoming detectable again. It is also possible that the star's magnetosphere, the region controlled by its magnetic field, changed in a way that allowed pulses to reappear. These are not settled answers. They are scientific paths to investigate. Why does that matter? Because pulsars are more than curiosities. They help astronomers study gravity, measure time map. Invisible material between stars and test physics under conditions far beyond ordinary experience. If some neutron stars can keep pulsing near the edge of expected silence, then the population of detectable pulsars may be more complicated than we thought. It also reminds us that radio astronomy is patient science. A telescope may hear nothing one year, then catch a rhythm later that changes the question. The fascinating part is the humility of it. A neutron star is only a city-sized remnant, but it can expose gaps in our understanding of matter, magnetism, and time. The takeaway is not that the mystery is solved. It is that the universe keeps leaving signals at the edges of our theories. And the next briefing goes even deeper into the mystery.